Intermolecular forces. When we talk about intermolecular forces, we'll refer to them as AF, which stands for attractive forces, or IMF, which stands for intermolecular forces. Essentially, the majority of intermolecular forces are attractive, so all molecules are attracted to other molecules. And this determines a lot about the molecule. For instance, solubility. In order to be soluble, your two substances have to have complementary or compatible intermolecular forces. And the way we refer to that is we say like dissolves like. The strength of the attractive force also determines melting and boiling point. Remember, for a substance to melt, it has to have enough energy to overcome the attractive forces between molecules and allow them to move. And then for a substance to boil, you have to overcome those attractive forces to the point where the molecules can separate from each other. But essentially, the stronger your attractive force is, the higher your melting point and the higher your boiling point. So if you consider substances at room temperature, say your substance is a solid, that has a really strong attractive force because room temperature means a fair amount of thermal energy. If you have a liquid, that's a weaker attractive force, right? Because then the kinetic energy of the particles at room temperature is about equal to the strength of the attractive force. And if you have something that is a gas at room temperature, that is the weakest attractive force between particles. And of course, there are substances that are solid up to way above room temperature. Those are very strong attractive forces, like the forces in metals and so on. Can you think of some examples of different substances? Like for instance, Cl2 is a gas at room temperature. That's got a weaker attractive force than Br2, which is a liquid at room temperature, which in turn has a weaker attractive force than I2, which is a solid at room temperature. There are several types of attractive force that we're going to explore. Let's start with one that is fairly easy to understand. Dipole-dipole attractions. In order to get dipole-dipole attractions, the two molecules involved must both be polar. So let's consider acetone. Acetone's molecular structure is trigonal planar around the central carbon atom. And the molecule has one polar bond between C and O. So there's your bond dipole pointing from the carbon toward the oxygen, which means you have a partial negative charge on the oxygen end and partial positive on the carbon. A pair of acetone molecules will be attracted to each other. The negative partial charge on the oxygen of one will be attracted to the positive partial charge on the carbon of another. Its simple opposites attract. And that attraction between those two molecules, again, is called the dipole-dipole attraction, and that's represented by that dotted line. Hydrogen bonding is actually a special case of dipole-dipole. That's the strongest kind of dipole-dipole interaction. In order to have hydrogen bonding, at least one of your molecules has to be a hydrogen bond donor. And what it means to be a hydrogen bond donor is that within the molecule, there is a covalent bond, X bonded to H, where H is hydrogen, and X is either nitrogen, oxygen, or fluorine. Here's a water molecule. This water molecule is capable of being a donor twice because it's got two bonds between hydrogen and oxygen, right? Oxygen is one of our possibilities. So what this essentially means is you have a very polar bond like that. A lot of partial positive charge on those hydrogens and a lot of partial negative charge on the oxygen. You also have to have an acceptor, which is any molecule that contains an atom with partial negative charge. So any molecule that is a hydrogen bond donor is also a hydrogen bond acceptor. So here, this water molecule is going to act as the donor, this water molecule is going to act as the acceptor. And that dotted line represents the hydrogen bond. We can add other water molecules to the picture. Notice this molecule that's a donor, or that was an acceptor, also has donor ability. And this molecule is also capable of acting as an acceptor when they're lined up appropriately. So we get another hydrogen bond. And here's a space-filling model of a bunch of water molecules hydrogen bonded to each other. Water is the substance in the universe that has, it's the one molecular substance in the universe that has such a low molar mass, but at the same time is liquid at room temperature. And water has a lot of amazing properties because it can hydrogen bond. Its molar mass is 18.02, but the hydrogen bonds are strong enough that it's liquid at room temperature. Every other molecule with a molar mass that low is a gas. Another cool thing about hydrogen bonding, when ice forms, because of the complex three-dimensional structure due to the hydrogen bonding, it is less dense than liquid water, and so it floats. Think about it. During an ice age, if ice didn't float, the oceans would freeze solid, and then all complex multicellular life would have died. But we've lived through multiple ice ages. Water is also good at dissolving lots of different things, especially ionic compounds, salts. Think about that. That's really good for us because we are like 70% salt water or something like that. Because water has the negative and positive partial charges, the negative can attract a cation, right? Because opposites attract. The positive can attract an anion. So let's say we make our cation look like this. A filled circle. And our anion is a larger empty circle, right? Because cations are smaller than the atoms that they came from, and anions are larger. Some solid ionic compounds adopt a cubic crystal lattice as shown here. Consider the cation in the lower right-hand corner. It is surrounded by 6 anions. The 3 shown, there's one above it, here, one behind it, one to the left of it, and then this cell is extended outward. There's one to the right, one below, and one in front. And you could do the same thing for the anions. Each anion is surrounded by 6 cations. Consider this anion here in the upper left-hand corner. Well, it's got a cation to its right, it's got one in front, it's got one below, and there's also one above up here. There's one behind it, and there's one to its left. Right, and then you could extend this crystal lattice outward in 3 dimensions until you have a chunk of salt that's big enough to see. Right. But water can get in there and disrupt those attractions and surround the ions. Here is a picture of a hydrated cation. You can see here's the cation in the center with its positive charge, and then the water molecules surround it and point their oxygen end toward it. So each delta minus on each oxygen is interacting with that positive charge on the cation. Here's a picture of a hydrated anion. You got the negative charge on the anion in the center, and now the water molecules are pointing their hydrogen bond donors with the delta plus charges at the anion in the center. So this is a hydrated anion. And so you can say, in this case, the water molecule is acting as a hydrogen bond donor and the anion is acting as a hydrogen bond acceptor. This is even stronger than normal hydrogen bonds, and we call it ion-dipole interactions. Stronger than hydrogen bonds because there is a full unit of positive or negative charge on the cation or anion, respectively. This kind of molecule that has carbons and hydrogens and nitrogens is called an amine. If you're a Breaking Bad fan, you've heard of methylamine. That puts the meth in methamphetamine. But anyway, it's got an NH covalent bond. That means there's a delta minus on the nitrogen and a delta plus on the hydrogen. The amine is a hydrogen bond donor. Now, this molecule over here is not an amine, it is a ketone, like acetone, but it has some negative charge on that oxygen and positive charge on the carbon. It is a hydrogen bond acceptor. So we can get a hydrogen bond forming between those two molecules. This means that the amine and the ketone will be soluble in each other. Take a look at these set of molecules here. Which of these is a hydrogen bond donor? Pause your video and answer. So if you've got the answer, I'm about to show it. Remember, a hydrogen bond donor contains X bonded to hydrogen, where X is either nitrogen, oxygen, or fluorine. right? So here's a nitrogen, here's an oxygen, here are lots of fluorines, right? Here's an oxygen, here's a nitrogen, and here are some hydrogens. The only place where we see one of these three atoms, nitrogen, oxygen, or fluorine, actually bonded to a hydrogen is in molecule B, right? It's this bond right here, the HO bond. So we have a delta plus and a very strong delta minus. So only methanol in this set of molecules is a hydrogen bond donor. So far the kinds of intermolecular forces we've looked at all have some kind of charge separation, right? Like you have ions or polar molecules. There's some permanent charge separation, right? Some permanent plus or minus. Substances that contain charge separation are soluble in water because of the ion-dipole effect. So substances that have charge separation are considered hydrophilic or water-loving. There are also substances that are nonpolar. Nonpolar substances have no permanent charge separation. Substances with no permanent charge separation include atoms and nonpolar molecules. So these substances are said to be hydrophobic or water-hating. So the big idea here is like dissolves like. Hydrophilic substances are soluble in other hydrophilic substances. Hydrophobic substances are soluble in other hydrophobic substances. But hydrophilic substances and hydrophobic substances do not mix. Like oil and water. If you put oil and water in the same cup and stir it up, you'll see the oil all floats to the top and the water stays on the bottom. Now, nonpolar molecules can still attract each other. Consider candle wax. Candle wax is solid at room temperature, which means it's got to have some pretty strong attractive force. However, candle wax is completely nonpolar. The reason that nonpolar molecules attract each other is called London dispersion forces, or just London forces for short, also known as van der Waals forces. And it's Dutch, so it's spelled van der, capital W-A-A-L-S. Van der Waals, pronounced van der Waals forces. So, you get London dispersion forces because all matter has electron clouds, and electron clouds are not static. So say this is the electron cloud of a molecule. I know it's been a long time since art school. But anyway, you got electrons kind of randomly distributed throughout it, and so there is no charge separation. But those electrons are whizzing around really fast and randomly. And at some moment in time, it might be possible to have a buildup of electrons on one end of the molecule or the other. And this gives us a small amount of negative net charge on this side of the molecule and a small amount of positive net charge on the left-hand side. So this is called a transient dipole. It only lasts for a few microseconds. Okay. Now when that transient dipole is in proximity with another molecule that starts out with even charge distribution, well, the electron buildup on the left-hand side, on the right-hand side of the transient dipole pushes on the electron density of the other molecule and moves it. Repels it. And so now we have, again, a sort of a dipole. And this is an induced dipole. Again, a lifetime of 10 to the negative 6 seconds or so. But in that brief instant, there is an attractive force between them, and we call it London dispersion forces, or LDF. London dispersion forces are very weak when the molecular mass is small. Consider helium. Helium has a very small molar mass of, what is it? 4? Anyway, helium atoms, you can cause them to liquefy. You can make a sample of liquid helium, but you have to cool it down to about 5 kelvins, right? So you really have to take almost all the energy out of those atoms in order for the LDF to be significant enough to cause condensation. But in general, you can say the heavier the molecule, the stronger the London dispersion force. Right? Remember we were talking earlier about chlorine, bromine, iodine? Well, chlorine, bromine, and iodine are all nonpolar molecules. Right, so there's chlorine. It's a gas at room temperature. Bromine is isoelectronic. It has an identical Lewis structure, but it's a liquid at room temperature. Why? Because bromine's bigger, and so its electron cloud is more polarizable. And then iodine is even bigger than bromine, even though it has an identical Lewis structure. So it is a solid at room temperature. And this is just an example of London dispersion force increasing as molar mass increases.